Today, I'm going to show you Bitwise operators and operations. We'll go into some examples later, but here's some things you need to know first. So, we have the following operators: AND, OR, XOR, and NOT. I'm going to show you the logic tables for AND. So AND basically means if you have two ones together, they make a 1. Anything else becomes a 0. So a 0 and a 0 becomes a 0. A 0 and a 1 becomes a 0. And a 1 and a 0 becomes a 0. So you can only get a 1 as an output if you put in both ones. In a problem, it's represented like this, no spaces in between. So if we have an x and a y, it becomes a z. And depending on what value the x or the y is, that's the z. So if you have two ones, x and y, it becomes a 1, z. But if you have a 0 and a 1, it becomes a 0. Likewise, if you have a 1 and a 0, 0. Still two zeros, well, that's still 0. This is it represented in a circuit diagram. This is the AND gate in a circuit diagram. Moving on to the OR gate, we have 0 and a 0 still makes a 0, right? But if there's at least one 1, if there's at least a singular 1, okay, maybe less confusing, you can get a 1 as an output. As you can see, 0 and a 1 makes a 1, 1 and a 0 makes a 1, and two 1s make a 1. So in equations, it's represented with a plus sign. So if that was 1 and 0, that would be 1. Or if it was 0 and 1, that's 1. If it was 1 and 1, that would be 1. But like the AND gate earlier, it's still going to be 0 if both of them are 0. Here's it in a circuit diagram. This is what it looks like. X or Y. That's how you read it. And it becomes Z. Next we have XOR. XOR is similar to the OR gate, judging from the name. So XOR is actually a shorthand for exclusive OR. What does that mean? So the exclusive, much like the name implies, it means that there should only be a singular 1 for it to become a 1. If there's two 1s, it's a 0. So look, two zeros still make a 0, right? Obvious. 0 and a 1 gives us a 1, like the OR gate. 1 and a 0 gives us a 1. But if you look here, two 1s gives us a 0. In an equation, it's written like this, fairly straightforward. X or Y equals Z, or X exclusive or Y equals Z. And here's it is in a circuit diagram. That's what it looks like. It's like a combination of the AND gate and the OR gate here. Next we have the simplest, I'd say, the NOT gate. We have X and not X. NOT basically just flips the value of the bit you're given. If you're given a 0 for the X value, and then you say not X, then you're going to have a 1. And if you're given a 1 for the X value, and you flip it with the not X, it just becomes 0. And this is what it looks like when it's written in a problem form. It's basically just the value, and then you put a bar over it. And this is what it looks like in a circuit. An arrow pointing with a little circle there. Now I'll show you some examples. We have two binary numbers and two hexadecimal numbers. So let's do the binary first. So let's say we have A and B. Or it could also just be written as AB, or A small and then B. It really doesn't matter, but you'd be seeing this format more often. So how do you do that? Well, they are of equal length, so you just write them down like this. And then, just like you do usually, you check to see if they're both 1s. If they're both 1s, then you make a 1. If they're both 0s, you make a 0. But if there's only one 1, then you still make a 0, because it's an AND gate. I'll write this here so it's not confusing. So 0 and a 0 makes a 0. 0, 0 makes a 0. 1 and a 0 makes a 0. Now we have two 1s here. That's a 1. That's 0, 0, so that's two zeros again. And then 1, 1. So that's A and B. This is our, I guess, C here. That's for the A and B. What if it was an OR gate? Well, similarly, you write the same thing. Oh, by the way, if they're not the same bit length, the process is the same. It's just that you bring down the numbers that don't have a match. So 0, 0 still makes a 0. But now we have a 1 and a 0. That means we can do a 1. Two 1s, that's still a 1. Then we do 1, 1, 1 all the way because there's always at least 1 here. So that's the answer for that. XOR, similar to OR. Two zeros, 0. 1, 1, 1. But there's two 1s here. Since it's two 1s, you do a 0. Then we have 1, 1, then a 0. Now, leading zeros here don't really count. It's only there for notation. So you can just remove that. But if the problem stipulates like at least 8 bits, then you can write leading zeros here. But for our purposes, this is fine here to show. And if you just say, let's do B, I guess. Let's do B for not. Say not 1, 1, 1, 1, 0, 0, 0. Well, that's just gonna be 1, 1, 1. And then we can just write it like that because all of these are just gonna be 0. Okay? And now, what if we had a problem that said AB and CD? What do we do here? Well, you can't exactly do these directly. So an easier method would be to just convert them into binary first. So let's do that. Let's do AB first. If you don't remember how to convert to binary, it's quite easy really. B, we know that's 11 and we know A is 10. So let's get our 11 value first. So that would be an 8 and then a 3. And then our A would be an 8 and then a 2. So that's our AB. This is our AB right there. And then our CD, our C would be 12 and our D would be 13. So 13 would be an 8 and then a 4. Then we would have a 1. There we go. Then our 12 would be an 8 and a 4 only. So here we go. And then if you just said this is AND, we just do the same thing. So that's 1, 0, 0, 1, 0, 0, 0, 1. And then we convert this back into hex. So our first number here, that's a 9. So that's, we can just write that as a 9 here. This is 9. And then our last number here, which is an 8. So we can just write it as an 8. So we can say that AB and CD is equal to 8, 9 in hexadecimal. And the process is also the same if it was an OR gate. AB plus CD. Remember, the plus just stands for OR. And we already have our values here, so we can just copy that. So again, bring down the 1, 1, 1, 1, 0, 1, 1, 1. Then we just convert that back. So these is a full thing. So that's F, because that's 15. Because 8 plus 4, 12, plus 2, 14, plus 1, 15. So that's F in hex. And then we have this, which should be 14, which is E. So we can say AB plus CD, remember this is an OR, is equals to EF in hexadecimal. Now, again, similar with XOR, 1 0 1 0, 1 0 1 1, and 1 1 0 0, 1 1 0 1. AB XOR CD. So that's a 0, that's a 1, 1 0 0, 1 1 0. You can just disregard that, but for simplicity's sake, let's just keep it there. So that's 0 1 1 0. That would be a 4 and a 2, so that's 6. And that's another 4 and a 2, so that's 6 again. So AB XOR CD is equals to 6 6. Last example here, the NOT. Let's just say NOT CD instead. NOT CD. Usually, by the way, it's in parentheses if it's not written with a sign with a value. So you could just say not Y there. But just to make things not confusing, not. We're gonna write that like that. So CD, as we know, is just equal to 1 1 0 0 1 1 0 1. Put the not there. And you just flip the bits. So 0 1 0 0 1 1 0 0. Because these two first are zeros, we don't have to look at that. So let's convert this. 0 0 1 0 is 2. And 1 1 0 0 is 3. So not CD is equals to 3 2